This is lecture 2D for Calculus 1 on continuity. We have been using the idea of continuity to find limits in the previous lecture. Now we're going to make a definition of continuity that is precise. Continuity actually has several layers. Or several levels. One is continuity at a point, continuity at an interval. Then we can move up to continuous functions, and then there's the idea of continuous extension at a point. The idea of continuity begins with a comparison of the value of the function and the limit of the function at a given point. Here's the definition of continuity at a point. A function f is continuous at the point x equals x naught if and only if the function is defined at x naught so that the value exists there. The limit of the function exists at x naught, and I'm going to call that L, and the limit and the value are the same. The if and only if part means that this definition works both ways. If a function is continuous, then the limit equals the value. On the other hand, if the limit equals the value, then the function is continuous at that point. There is a slight difference in how we word continuity depending on whether this x naught is an interior point or an end point. If it's an interior point, we require that we have both right and left hand limits and that they're green, and we say the function is continuous at that point. If x naught is at an end point, we only require a limit from either the right side or the left side. In those cases, we would say f is right continuous if all we required was a right-sided limit, or f is left continuous if all we require is a left-handed limit. I want to make a remark now about piecewise functions. For these piecewise functions, always look, if you're checking for continuity, always look at the point that is a boundary between the two domains, the two subdomains of the pieces. In this case, x equals 0 is the point in question. The limit has to be the same. The limit of g of the first function as x approaches 0 has to equal the limit of the second function h as x approaches 0. In those cases, if you looked at the graph, you would have one piece and then it would immediately change to the other piece, and then there would be continuity right at the point where you change from one piece to another in the piecewise function. Of course, if a function can be continuous, it also could probably be discontinuous. The discontinuities are sort of a mirror of discontinuities, or a mirror of problems that occur in limits. I'm sure you recall the oscillatory discontinuities, or problems with oscillation and taking limits. If a function oscillated so wildly that there was no endpoint to the trend of those oscillations, then no limit could be assigned. In that case, the function cannot be continuous at that point either, since it does not have a limit. So our function sine 1 over x has an oscillatory discontinuity at x equals 0 because it does not have a limit there due to its oscillation. For the infinite discontinuity, there is now another little discontinuity between limits and continuity. If a function, if the limit of the function approached infinity, we say the limit is infinity. If you remember, I said we agree to say that the limit is infinity. When it comes to continuity, though, if that limit is infinity, we don't accept that. If the function has a vertical asymptote, we say it's not continuous there. We can't match up a value at infinity with a limit at infinity. So if there's a vertical asymptote, we say the function isn't defined there. We say the function is not continuous there. So here's a rational function, f of x equals 1 over x. It has an infinite discontinuity at x equals 0. If you took the limit as 1 over x as x approached 0, you would say that limit equals infinity, but that's not good enough to be used in the definition of continuity. So here are two ways to be discontinuous: an infinite discontinuity occurring at vertical asymptotes, or an oscillatory discontinuity where a limit cannot be assigned. Limits can't be assigned either at jumps. In such places, we say the function has a jump discontinuity. In those cases, you may or may not have right and left-hand limits, but the bottom line is the right and left-hand limits don't agree. Okay, you probably remember the Heaviside function, the one that was used as a switch. In this case, at x equals 0, there's a jump. the function is not continuous at x equals 0. Similarly with the signum function, there is a jump at x equals 0, therefore the function is not continuous at x equals 0. This function is discontinuous at every point. It's 1 if x is rational and minus 1 if x is irrational. Obviously, right next to every rational number is an irrational number, so this is a very discontinuous function. If you have a situation where you have a discontinuity because the limit exists but the value is a problem, then you can remove that discontinuity by assigning the limit, if it's finite, as the value of the function. This is called making a continuous extension. So let's just look at interior points. The right and left hand limits must exist and agree, but the value of the function perhaps is not defined at that point, or it does not agree with the limit. This function sin x over x is not defined at x equals 0, because when x equals 0, you would be dividing by 0. Obviously, it's not defined there. But it has right and left hand limits at x equals 0. And the value of those right hand and left hand limits are both 1. So you can extend this function into a continuous function at that point by creating this piecewise function. You let the piecewise function be defined as sin x over x everywhere except at the problem point. At the problem point of x equal 1, you assign the limit. Here's another example. If you recall from the last lecture on finding limits, we showed that 1 minus cosine x over x squared was not defined at x equals 0, but by the squeeze theorem, it has a limit there, and that limit is 1/2. The continuous extension is the piecewise function that is equal to 1 minus cosine x over x squared every place but at x equals 0, and at x equals 0, it has the value of 1/2. So here's a graph of the situation. The red line is 1 minus cosine x over x squared. It's not defined at x0, but I defined it to be 0.5 at x equal x0, making a continuous function out of it. All of that discussion was for continuity at a single point. If the function is continuous at every point in an interval, we say the function is continuous on that interval. If the function is continuous at every point in its domain, we call it a continuous function. Now this gets to be a little bit troublesome, or appears to be a little troublesome for some functions. Look at the tangent function. It has an infinite discontinuity, a vertical asymptote, at multiples of pi over 2. But tangent is still called a continuous function because it is continuous on every point of its domain, and those problem points, x equal pi over 2, have already been thrown out of the domain. This is why we can also call a rational function continuous. So if we have just our prototype rational function 1 over x, it has an infinite discontinuity at x equals 0, it is still called a continuous function because it is continuous at every point on its domain, and the point x equals 0 is excluded from the domain. Previously, in algebra, continuity was described, it wasn't defined, it was described as relating to the graph of the function. It was said if you could draw the graph of the function without lifting your pencil from the paper, it was a continuous function. And we all know that's very imprecise, and in fact you could think of all kind of ways around it. If you have any kind of imagination, you can figure out all ways around that kind of definition. It isn't even a definition, it's just sort of a description or an idea. Now we have a precise definition of a continuous function. We start with continuity at point. If it's continuous at a point, the limit equals the value. If it's continuous on an interval, it's continuous at every point in the interval. And a continuous function is one that is continuous at every point in its domain. Here's a list of continuous functions, some you know very well. Polynomials, exponentials, absolute value functions. They are continuous everywhere because their domain is all the real numbers. Other continuous functions are logarithms. Remember that vertical asymptote at x equals 0 is excluded from its domain. Rational functions are continuous on their domains. Algebraic functions, the trig functions, of course, sine and cosine, are continuous everywhere. And inverses of continuous functions are continuous. That's why you see exponentials and logarithms both as continuous functions. Continuity can be inherited in the sense that algebraic operations on continuous functions yield continuous functions. The reason we like continuity is is that if you want to find the limit, all you do is go and find the value. You just evaluate the function there. And there are other attributes of continuous functions that are important in mathematics. So these algebraic operations just yield more continuous functions. We're going to start looking only at a point, x equal x naught, and say we have two functions, f and g, that are continuous there. So what this means that algebraic operations yield more continuous functions is this. If I make a linear combination of the continuous functions f and g, the result will be a continuous function. By a linear combination, I mean taking two constants, alpha and beta, and multiplying f and g by them, and then adding. So you've got alpha f plus beta g. That is still going to be a continuous function. If you multiply the two functions together, the result will be a continuous function. Division works too, as long as you're not dividing by 0. You can take roots and powers of continuous functions, and you'll still get a continuous function. And functions are continuous under composition. So I'm going to just show you a little sketch of the proofs for continuity under multiplication and continuity under composition. The proof of continuity under multiplication follows directly from the product limit law. Right? So if f and g are continuous at a point, I know that the limit at that point is the value for f, and the limit at the point for g is the value of g. When I'm taking the limit of f times g, that is just the product of the two limits. With substitution and a little change in notation, there I have it. So if you take two continuous functions, you multiply them together, you get another continuous function. Of course, when you're talking about, all I've talked about here is continuous at a point. If you're talking about the functions being continuous, you must define what the domain is. And when you multiply two functions together, when you do these algebraic operations, the domain of the result is the intersection of those two domains. So you can only look where the domains overlap. That is where the new function f times g is defined. And that is where it is continuous. I will now attempt to transmit a proof of continuity under composition. I think it's probably very hard to read from a lecture of this sort. But I'm going to try anyway, and I hope that you can just get an idea of how these sort of things are set up. So we're going to take a function f that's continuous at some point a and x, and let f be a mapping from x into z, say. And g is a function, and it's a mapping that maps from y into x, and it's continuous at the point b. And the limit as y approaches b of f of y is a. That is a value that f is going to pick up and map into z. So by the continuity at f at a, that means that there is, for every epsilon, there is a delta. I'm just going to call this delta delta 1, and I'll show you why in a minute. This is just the definition of continuity f. That f of x minus f of a, because f of a is now its limit, it's the value there, is less than epsilon whenever x minus a is less than, I'm calling it delta 1. I'm going to make a similar statement for g. By the continuity at f at g, for every epsilon, but I'm going to call this epsilon 1, there would be a delta such that g of y minus a is less than epsilon whenever y minus b is less than delta. Okay, and I'll show you the setup, and this is the most important thing to get out of this. When I'm looking at continuity, I want to end up with my epsilon and deltas. If you remember, when you do composition, it's really a two-step process. You go from y to g, and then you pick up and go from, you go from y to x with g, and you go from x to z with f. With composition, you want to start all the way in y and get all the way to z. But we have to do it in two steps. All right. I'm going to have this epsilon here will show the tolerance in z. This shows the tolerance in terms of the independent variable over in y. But I have that intermediate step in the middle, the step in the set x. And so what I've done is call that delta 1, and here's epsilon 1, and what I'm going to do is merge those two, and then by the continuity of g, they will disappear, and all you end up with is the epsilon and the delta that you wanted. So here's how I do it. Because epsilon 1 is arbitrary, I can say, why not let it equal delta 1? So now I have this. Okay. Epsilon 1 can equal delta 1. It can equal any value it wants. And I can always find some delta. Now because y is continuous, f at y equals x, it's a mapping from y into x, rather, I can write this as x minus a is less than delta 1 when y minus b is less than delta. This is the result I was looking for when, by definition of continuity, f of x is f composed with g of y, because they're because of composition. I assign that as the endpoint, and here I have my final result in terms of epsilon and delta. So I'm going to attempt to draw a picture of this using these tools. This might be a dismal failure, but let's try it. Okay, I'm going to pick up a black circle. So here, oh, I didn't pick it up. Okay. Okay. So I have 3 domains, or rather 3 sets. This is the set y. This is the set x. And this is the set z. All right. Now, G maps from y into x. This is G. Let's try to write a G there. Okay. F maps from x into z. This is my F. With composition, I'm going to start all the way here in y and go all the way over here to z. So you can see from this last statement that I'm saying, okay, that's the statement right here. F of g of y minus f at a is less than epsilon whenever, change color here to, whenever y minus b is less than delta. Well, y minus b less than delta is a statement about this set way over here. That's how I got this continuity under composition. I have to show that this function, which is f composed with g, is continuous when f and g are continuous at that point. X0 is inside that yellow square and inside that kind of blue square. And to do that, I had to use a continuity of f, I had to use a continuity of g, then I had to merge those definitions that were in x and get rid of them, and then I ended up with a continuity all the way from set y to set z. I realize a proof like this is hard to follow on this lecture when I can't be writing things out as I go along. So that's continuity. Definition is, if it's continuous at a point, then the limit equals the value. If you want to find the limit of a function that is continuous at a point, all you have to do is evaluate the function.